Okay, so we're looking at discrete time Markov chains, and one of the questions we commonly want to ask is, what's the behavior of this process if it runs for a long time? So we're going to look at a thing called equilibrium behavior of Markov chains. And what we're going to do is we're going to start with an assumption. We're going to assume that as time goes on, if we look at lots of steps, remember this notation, Pijm, is the probability of going from state I to state j in m steps. We're going to look as m gets bigger and bigger. So we're looking at lots and lots of time steps. We're going to assume that it basically reaches a constant value, which we'll call pi j. There's two things to note about that. First of all, we're saying that the probability of being in state j after many steps converges to some constant value. It doesn't vary. And I also notice that the pi j doesn't have an I in it. It's now independent of where we started. So you have this process, you run it, and after a certain amount of time, long enough, we find that it just hits this steady state. And we can show that the equilibrium equations that control this is pi equals pi, and we've got our one-step transition matrix. Where pi is, the first entry will be the probability of being in state 0, then pi 1, pi 2, so the state 2, state 1, state 2, etc. So where does this come from? So let's think about what we could do. Well, what we could do is we could break it down and look at a single step. So what we're going to say is we're going to say the probability, let me start again. The probability of going from I to j in m steps. Well, we could actually say, well, look, first of all, what we could assume is that we could split over all the possible states using the law of total probability. This is the same as the probability from going from I to k in m minus 1 states, and then finally we go from k to j. So I've taken the journey from I to j and I've split it down. In the first m minus 1, I make a journey all the way up to k, and k could be any possible states, and then I go from that state, and in the final step I jump to j. What are we looking at? We want the limit as m goes to infinity. On the left hand side, that's Pijm equals the limit as m goes to infinity of our summation. K in all possible states, Pik m minus 1, Pkj. But we have decided by our assumption that this is just going to be pi j. I'm going to assume that I can interchange these two things. In this course, I'm not going to show, or this video, I'm not going to show that that's achievable, but we'll assume that it is. And then we've got now the summation as k is in s, and we've got the limit as I goes to k in m minus 1. Well, as m goes to infinity, m minus 1 also goes to infinity. So that is just going to be pi k, because that's our steady state by our assumption. And then we've got our final term Pkj. Well, if we now looked at these summations and thought about it for each individual state, that's exactly the same as taking that vector is equal to the left multiplication of our row vector times our transition matrix. So that's where that came from, this sort of steady state behavior. Further, we're going to assume that if when I have this vector of pi i's and I add them all up, I get 1, we're going to call that our equilibrium probability distribution of this discrete time Markov chain. So if I can find a solution to this, such that this vector of pi's equals the vector times the p, so we've got this steady state, and also when we add up all the elements in that vector pi, we get 1, we've got this what we call equilibrium probability distribution. Let's have an example. We're going to look at a very simple queue. And first of all, we're going to say that for most of the states, so our states is going to be how many people in the queue, it will occasionally increase by 1 with a probability p. It will decrease by 1 with a probability q. And finally, you stay the same size in a time step with 1 minus P minus Q. So we're looking at this Q, and we might look at every minute and we count how many people, and every so often it will go up or go down or stay the same. If the Q is empty, it can't go down, so we'll just say it can increase by 1 with probability P and stays the same with probability 1 minus P. So here's my state diagram. We start at 0, and then in every time step there's a probability no one turns up, but there's a probability P that we increase it by 1, and we've got all these P's of increasing by 1. And every so often we can decrease in a time step by Q, and we have the 1 minus P minus Q that we stay the same size. So we're going observing this Q, and we've made an assumption that it only ever Qs when we measure it by going up by 1 or down by 1. You don't sort of have enough time that you come back and it's suddenly got 4 more people in there. So what's our states? Well, S is going to be how many people in the queue, so that can be 0, 1, 2, 3, all the way up to infinity. And for 1 and greater, we have the probability of going from state I to state I plus 1, so increasing by 1 is P. Going from I to I minus 1, the probability is Q, and going from I to I is the 1 minus P minus Q. While with 0, the probability of going from 0 to 1 is P, and the probability of staying at 0 is 1 minus P. And if you think about it, you can get your steady state. Because if we look at this, well, pi 0. What's the probability of being in state 0? Well, either I could have been in state 0 and I could stay there, or I could have been in the state above and I could have gone down. While at the other states, let's think about the pi I. So what's the probability of being in state I? Well, I could either be 1 less and someone arrives, I could be at that value and I stay the same, or I could have 1 more in the queue and someone leaves. So there's our Q equilibrium equations. And when we solve that, we could get our stationary distribution. So how can we interpret this stationary distribution? Well, there's 3 interpretations that you can look at. The first one is what is called the limiting. And what we're saying is that the pi j's is the limiting probability of the process being in state J. So what we're saying is if this process has run a long time, and you randomly choose a point and look at it, the probability you're going to be in state J is this pi j. The next one is what we call stationarity, which is if this process has run a long time, that equilibrium distribution is going to be the probability distribution of the process. Now this is one of the most useful ones for me, because sometimes what I'd like to do is I would like to have a random variable from an arbitrary distribution. And if I can set up a Markov chain such that the values, the states, have the same equilibrium distribution as an arbitrary distribution I want, then they will look like that distribution. And this is the thing called Monte Carlo Markov chains. So you choose the correct Markov chain, which will give you the required distribution that you would like to sample from. The final one is called the ergodic. Basically, this means that if the process has run for a long time and you looked at what proportion of the time you were in state J, that would be approximately equal to pi j. So you've got the 3 interpretations of that equilibrium distribution. Next time, we will start to look at how you actually obtain the equilibrium distribution.